Continuing on here with electron configuration, which is really what we're going to be writing. This again is the order at which electrons go. The order at which electrons go into the atom, and they are filled based on. We do write electron configuration based on filling order, which is always lowest energy to highest. And you always start when you're writing electron configuration, as I mentioned before, right here at this top. And once again, you always just want to kind of keep zigzagging back and forth until you filled in everything that you need. So at the end there, we talked about how you could kind of really easily sort of create this for yourself. So that's a good way to either remember how to create it or just remember it so that you do have the right order. Again, with the S is 2 electrons max, P subshell 6, D subshell 10, and our F subshell 14. So let's get into writing some of this configuration. Here's a figure from your book that again shows the order. And this is usually, again, where people get tripped up is that S to D transition. So again, always the S before the D when you're doing it. So electron configuration is basically the order at which electrons have gone into the atom, going in from lowest energy level to highest, and again, stopping when it is filled. To figure out how many electrons something has, it is based on the atomic number. And we could use the atomic number to help us out, even though the atomic number is the number of protons. If it is a neutral atom, as we talked about before, you have to have an equal number of protons and electrons. So the atomic number will also give you the number of electrons if it's neutral. Obviously, if it has to have a charge, you just have to adjust some things. But things that are neutral, you could go with how many protons there are. We'll give you how many electrons that there are as well. So let's just start with the pretty simplest one, which is hydrogen. So hydrogen has 1 proton, which means in a neutral hydrogen, it has 1 electron. So once again, referring back to our little chart here, we're going to start up here at top. And that's going to take us to our very first orbital on the first energy level, which is 1s. And for hydrogen, what we would write is 1s1, and that would be the electron configuration for hydrogen. The first number here is the principal quantum number. That's that n number. The right here is the orbital, our subshell that the electron is hanging out in. And at the very top is the number of electrons there are in an orbital, our subshell. That is the proper way to write electron configuration 1s1. And what I mean by that is the 1s and the second one, there's a superscript up on top. It shouldn't just be all big numbers, 1s1. There's also no commas people like to put for some reason in between everything, no dashes or anything crazy like that. So just 1s1 is the proper way to do that. Another way that we can represent electron configuration is by drawing what is sometimes referred to as the orbital diagram. And the orbital diagram is either boxes or lines that represent each orbital. So for hydrogen here, that would be the 1s box, or the 1 line to represent the 1s orbital. And when we put the electron in, it always is filled pointing upwards. So we use arrows to represent the electrons, and in this case, pointing upwards in that particular orbital is how the first electron always goes into the orbital. So always in that sort of upwards position is where you should kind of point the arrow. And again, that arrow represents the 1 electron that is in there. So that is orbital diagram, not to be confused with draw me a picture of the orbital, what it looks like, the S, circle or figure 8. So when they talk about orbital diagram, again, it should be boxes or lines and arrows to represent the electrons that you put in there. Any questions so far? So that's hydrogen. Obviously, as we can see here, we have room for 1 more in that box, right? As each of these orbitals can only hold 2. So we have a place to put 1 more before we would have to move on to the next one. So that is, I almost drew it perfectly. Now, there is a rule in terms of what happens next in terms of how we put the electrons in. So there's an important rule which is known as the Pauli exclusion rule. And the Pauli exclusion rule says that no two electrons could have the same four quantum numbers. Now, although we don't talk about the other quantum numbers here, the way that we get around that is how we place the electrons in the orbital, and they're placed in opposite what is referred to spins. Electrons have spins associated with them. So if we look at our orbital there, our next electron could have really two ways we could put it in. We could put it in the same direction, or we could put it in opposite directions. The way that the second electron goes in, based on the Pauli exclusion rule, is it does not go in the same direction. So it always goes in opposite directions. This electron that is pointing upwards has what is referred to as a spin quantum number of +0.5. This guy here has what is referred to as a spin quantum number of -1/2. And that little difference, for example, gives each of those electrons different quantum numbers. So to illustrate why they would have the same quantum numbers, I'm just going to tell you what the quantum numbers would be in this situation, and you don't have to worry about figuring them out. But if we took, for example, our electron that is going in this one, and it's in, say, the 1s orbital, the n value, as we know, would be n is equal to 1. The L value, which basically represents the type of orbital that the electron is in, would have a value of 0, and a 0 represents an s orbital. The m sub L, which is another quantum number, would have a value of 0, which means there's basically just one s orbital. And the m sub s here would be +1/2. And those would be considered what is referred to as the four quantum numbers for that electron. You do not have to figure out the four quantum numbers for the electron. You'll do it in 1A. But this is just to illustrate why if we put this second electron in the same direction, it would actually end up with the exact same numbers. Obviously, this guy is also on the first energy level. That is also sitting in an s orbital. That is also one type of s orbital. And because it's pointing upwards, it will have the same spin, which means electron on the right and the electron on the left have the exact same four quantum numbers, which is a violation of Pauli's exclusion rule. The way that we get around that is really when we look at the electron on the right heading in the downward direction. This is still in the 1s orbital, which means it's n equals 1. It is still in the s orbital, which means L equals 0. It is still only one of them. But the difference now is it's actually pointing downwards, which means the spin is -1/2. And that difference in how the electron is spinning in that orbital allows that electron, when it's pointed down, to have different set of quantum numbers. They're not all four the same. So that's what is meant by Pauli's exclusion rule, that no two electrons that occupy the same orbital can essentially be pointing in the same direction. So they can't both go up, they can't both go down. They always have to go opposites of each other if they're sort of sharing the same orbital. Any question on that? So what that means is when you fill orbitals, first one in, always up, second one in, opposite, to kind of pair it off and match it. Any questions on that there? And again, you do not have to figure out L, M sub L, and M sub S, and all that kind of stuff. You do need to know the N, because the N is basically just the energy level, and that's the first number there. So then let's talk about when this happens. This happens with helium, which is the second electron, has 2. So once again, we would come back to our chart, and we would start up here. We would come here to our 1s orbital, and we would put it in as 1s2 in this case. Once again, this first number tells us we're on the n equals 1 level. Our electrons hanging out in our s orbital. And now we have not 1, but 2 electrons in that orbital. And we could also draw our orbital diagram for helium. Again, the first electron goes in, second electron goes the opposite way, going down. This is what is referred to as the spin being paired. So that pairs off the spin. As we saw there a second ago, one has kind of plus a half, one has minus a half. So they're opposites of each other. So they're all paired up. And that is always how a filled orbital should look. If you draw an orbital diagram, should always have electrons, or arrows in this case, heading in opposite directions. They again should never head in the same direction. Any questions on that one there? All right, looking at the next one, continuing on to lithium, which is 3 electrons. So once again here with lithium, we're going to start at the top. So that's going to take us to here, which has 2 electrons. And from our orbital diagram, can we put any more electrons in that first box? We cannot, so we need to continue on, and also then come to here is where we're going to go next. So we will have 1s2 and now 2s1 in this case. This has 2 electrons on the first energy level. It also has 1 electron on the second energy level, right? Or n equals 2. And we could count the top number. There's 2 electrons in the first guy and 1 electron there in the second. And if you count the top numbers, that's 3 total electrons, which is all of them. We could draw our orbital diagram for lithium here. And I'm not going to draw it correctly in terms of energy. Obviously, in energy, you just kind of keep going upwards, like our kind of lines that we had earlier to save room. I'm just going to go side by side, but normally, you kind of draw it with the energy kind of going upwards. So we would need a box here for 1s. We would also need a box or a line for 2s. And our electrons would go in once again. First guy will go up. Second guy will go down. First guy here on the second one will go up in this case. And that would be our orbital diagram. We could also see here, before I need to move on to the next orbital, I could still have room to put 1 more electron there in the second s orbital, right? So I have room to put 1 more in there before I would have to move on. Any questions on that? Again, here, no commas, dashes, should just be 1s2, 2s1, and that's the way that you refer to that. So continuing on, the next one there is number 4 on the periodic table. And that is beryllium. So beryllium has 4. So once again, we're going to start over here. It's going to take us to our 1s, which we filled. We now will go to our 2s, where we do have room for it to put it in there. So we'll do this. This will be 1s2, 2s2. It now has 2 electrons on the n equals 2 level. It has 2 electrons on the n equals 1 level. Doing our orbital diagram for beryllium, once again, we'll need 2 boxes, a 1s box and a 2s box. And again, normally they would be drawn more of like energy upwards, but we'll go up and down, up and down. Can I put any more into that 2s at this point? I am filled at this point, so more electrons will have to go to the next lowest energy orbital at that point. Any questions on that so far? Continuing on then, might as well. Number 5 looks like boron there. Looks like a winner. Let's take a look at that. So boron has 5 protons, which means a neutron will have 5 electrons. So again, we're going to start here, and that's going to take 2 of the 5. Coming back this way, that will take 2 more of the 5. That means we then need to end up over here to our 2p orbital at that point. So its electron configuration here would be 1s2, 2s2, 2p1 in this case would be our electron configuration. And that means that on this particular case, how many electrons are on the second energy level? Second energy level is all those guys. So on the n equals 2 level, there are 2, and 1 more makes 3 electrons on the second energy level. On the first energy level, which is this first number, there are still 2 electrons present on that one. Our orbital diagram will look a little bit different here with boron. We have a 1s box. We got a 2s box. And for our p, because it's a p subshell, and there are 3 different p orbitals, you need 3 boxes or 3 lines. This represents the px, the py, and the pz orbital. So you actually will have 3 boxes. So we would go up, we go down to fill, we go up, we go down to fill. And now in this case, the way we fill it is we go left to right. So the electron will actually end up in the px orbital, heading again in the upwards direction. Any questions on that there? At this point, we do have some options. We could put how many more electrons into our p subshell. Again, this is our p subshell here. We could put another 5 before we're completely full, right? So it could really fill it up with a lot more electrons. Also shows that you do not have to completely fill up a subshell. You could just put as many electrons in there that you need in this particular case. So we also have some options as to where we could put the next set of electrons. And there is a rule that we want to follow when we talk about where we should kind of place those electrons. And that rule is what is referred to as Hund's rule. And Hund's rule says that the most stable arrangement for electrons in a subshell is the ones that maximize parallel spin. So parallel spin is different than what we saw here, which is paired spin, where they go opposite. Parallel spin means that they go in the same direction, would be parallel spin. So when we look at just our, say, 2p subshell and our 3 boxes, which is our px or py or pz, the next place that we should put the electron is actually here, and that's going to maximize the parallel spin, because if we put it in the first one, that's paired spin, right? So that's not maximizing it. So the way that electrons go into a subshell where there's multiple orbitals is they will go in one at a time, and then when they run out of room, then they'll go back and start pairing up. So they always go in one at a time in the upwards direction, and then they come back and pair up on the end there until obviously they're all full at that point. Any questions on that? So that occurs here at carbon, which is number 6. So carbon has 6 electrons. So once again, we're going to start over here. That's going to take care of 2 of the 6. Coming back this way, that's going to take care of 2 more. And we have plenty of room for those last 2 into our 2p. So that's where we're going to end up as well. So we will have an electron configuration of 1s2, 2s2, 2p4, not 4, but 2. And if we count up the top numbers, that's 2, 4, and 6, which is the 6 electrons. Again, here on the second energy level, we have 4 electrons. On the first energy level, we have 2 electrons. Coming back to our orbital diagram here and our boxes, so we have our 1s, our 2s, and our 2p, which is again our px, py, and pz. Up, down, up and down, up, and the next one more over into that box is how we should do it. Again, maximizing that parallel spin, which is going to make it more stable. Any questions on that one there? All right, so we might as well finish out the first 10 here. So nitrogen comes next, which is number 7. So looking at nitrogen, which is 7. Once again, we will start here. 2 could go there. 2 could go there. And we still, again, have room for all 3 of them into there. So that is where we will stop. And that will give us 1s2, 2s2, 2p3 in this case, which is 7 total. Once again, on this case, we do have 5 electrons in the second energy level and 2 electrons in the first. Our orbital diagram for nitrogen, 1 up, 1 down, 1 up, 1 down. And our 3 for our 2p subshell, 1 up, and last one up over there. At this point, we have nowhere to go but to start pairing them off. So we pretty much maximize all the parallel spin that we could do. And any more electrons will now have to go back to that first p orbital and again start pairing everybody up. So let's take a look at that. That is our next element there, which should be oxygen, I think. Oxygen is 8. And again, with oxygen, which is 8, we will go 2 there, 2 more there. This is 4, and 4 more into there, which we can, because again, a p subshell could hold 6 electrons. So we're only up to 4. So we have room for it. So we'll do our 1s2, 2s2, 2p4. Which will give us 8 total electrons. At this point, we actually now have 6 electrons on the second energy level and 2 on the first. So continuing on here to our orbital diagram, we will have 1 up, 1 down, 1 up, 1 down, and now with our p, again, it will go 1 up, 1 up, 1 up. And now we're going to come back and start to pair off here at the first one. By doing that, it's still maximizing the parallel spins that's left in the last 2 orbitals by having those 2 still kind of upwards rather than pairing those off as well. Yeah. It changed to 4 because oxygen has 8 electrons. So 2 of them will end up in the first orbital. 2 of them will end up in the second s orbital. There are the 2s orbital. That's 4 total electrons. That means that there's still 4 that needs to go somewhere. The next lowest set of orbitals are the 2p subshell, and they could hold a maximum of 6. So we only need 4 there, right? So 4, 2, and 2 is 8 total electrons, and that would represent the 4 that we see here with the arrows on the right there. So those are the 4 that end up there at the end. Other questions? All right, so to fluorine, which is number 9. Take a look at that guy. So fluorine, which is 9, once again, starting up here, that's going to take care of 2 of them. I'll take care of 2 more, which is 4. And now, because he could hold 6, we could put the 5 that we need to go into our 2p subshell. We do not have to proceed any further at this point. So our configuration 1s2, 2s2, 2p5. Once again, if you're not sure, you can count up the top numbers, and that again is the total number of electrons that you have placed, basically. So 5 and 2 is 7, plus 2 more is 9 in this particular case. And that means that our orbital diagram will look something like this. So 1 up, 1 down, 1 up, 1 down, up, up, and up. Now coming back and pairing them off will look something like this. Now we could clearly see we are almost filled with our 2p subshell. We have basically 1 more spot there at the end to put 1 more electron in there. And that obviously happens here at number 10, which is our neon. And let's take a look at neon and fill it up here. So neon, which is number 10, will take us once again starting here. 1s takes care of 2, takes care of 4, and now we could put all 6 of them into there, and that definitely will fill up our 2p subshell. And that means that our electron configuration would be 1s2, 2s2, 2p6 in this case. We have 8 electrons on the second energy level Again, still 2 electrons there on our first energy level. Looking at our diagram here, we're going to go up and down once again, up all the way across, coming back down now and pairing off everybody. And we can see now that we have completely filled up our 2p subshell, which means if we needed to fill more in, we would then go off to the next one, which would be R3s at that point to put electrons in. Any questions on that there? Yeah. No, so if you had at the end the last of your configuration like we had there at 2p2, it is always when you have multiple orbitals. Again, all these individual orbitals, which are represented by the boxes, are referred to as a subshell or sublevel. Whenever you have multiple electrons that need to go into ones where there's multiple orbitals together, they always go up first in each box. And only when you reach sort of the end of all the orbitals, then you got to go back and start pairing off. So always one up and then come down. So in the case of 2p2, you would just have, like we had earlier there, it would look something like that at the end, just like that. Yeah. Other questions? All right, so why don't you do the next one, which is the electron configuration for argon, which is 18. Okay, let's take a look. Coming back here, here at 18, we got to go through our list here and just kind of think about where we're going to end up. We will come here, which will give us 2, come this way, which will give us 4. We could put 6 there, which would be 10. We then would have to proceed here, which would be 2 more, right? Which would get us to 12. And we also then need to come back this way and put 6 more into there, right? To complete it out. So we got a little further to go on that one. So let's take a look here. That's going to get us 1s2, 2s2, 2p6. Again, we're going to go to 3s2 and 3p6. Once again, if we count the top numbers there, we got 18 happening. In this case, on the third energy level, we have 8 electrons, right? So on that third energy level, we have 8 electrons. On the second energy level, we also have 8 electrons. And on the first energy level, right, we have 2 electrons. So clearly here, if we were going to do our orbital diagram, we need a bunch of boxes happening. And obviously here, up and down, one at a time in the upwards direction, and then pairing it off, up and down. Again, over here, one at a time, and coming back and pairing it off. Yeah. Any questions on writing that electron configuration? Okay, so let's talk about a couple of things and a couple other ways that sometimes electron configuration is sort of written. As you can see here, this is a little picture of the sort of the ending of part of each of those electrons configuration, how they end. An idea which is referred to as the off-ball principle is based on the fact that protons are essentially added one at a time to our atom, and that is sort of the build-up principle. Electrons, again, are also added in a similar fashion, one at a time, until we basically fill it all up. Again, lowest energy to highest energy when we do that. So if we take a look at potassium, which is 19, potassium's electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, and a reminder that after the 3p6 it actually does go to the 4 first. So 4s is next. If you look at our little chart there, and it would be 4s1 in this case, which would be the electron configuration for potassium. When we look at this electron configuration up through here, this part of the configuration is 18 electrons, right? And we could get that by counting the top numbers. So you have 18 electrons. And as we saw just a second ago, 18 electrons is argon's configuration. So you actually can do sort of a shorthand for electron configuration. And we could also write this as argon. And that little brackets with argon in the middle indicates its electron configuration for argon. And then we just continue on as 4s1. Argon is a noble gas, and sometimes referred to as noble gas configuration. You put always the noble gas in brackets that come right before whatever element you are going to write it for. So obviously, if you look at potassium and go backwards on the periodic table, argon, which is group 8, is the one that comes before it. If we look at something like magnesium, which is 12, its electron configuration would be 1s2, 2s2, 2p6, 3s2. Once again, if we look at magnesium's configuration up until this point here, that is 10 electrons. And if we look at the periodic table, 10 electrons is neon, which is the noble gas that comes right before it on the periodic table. And we could kind of shorthand this guy as neon and continue on with 3s2. So it always has to be a noble gas that goes in the brackets. So it's always got to be a noble gas. And you could kind of do a shorthand version here of it. Question on that. So you can write the electron configuration either way, unless it says don't do that. But you can write it either way. And again, when you see that bracket, it is that noble gas that comes right before it. Any questions on that part of it there? So let's talk a little bit about what happens, though, if we do have something, say, with charges and how that affects the electron configuration. So let's take a look at some of these representative guys and say they had some charges. So let's take a look at, we'll do potassium since it's here. If we do potassium, but we do potassium with a +1 charge, because it has a +1 charge, that means it has lost 1 electron, right? That's why it is positively charged. That means potassium with a +1 charge actually will have 18 electrons, right? Instead of 19. That means when we write the electron configuration for potassium with a +1 charge, it would be 1s2, 2s2, 2p6, 3s2, 3p6. That once again is 18 electrons, which means that is argon's configuration, right? So that is the same configuration as argon. If we look at our, say we'll look at, take a look at sulfur, for example. Sulfur, which has no charge, is 16. Its electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p4 in this case. And if we look up to here, that's actually neon's configuration. So that's what you would continue on if you wanted to do sort of noble gas configuration. You go neon, 3s2, 3p4. Now, if we have sulfur that has a -2 charge, that means that it has gained 2 electrons. So you have to add that to your total for sulfur. So sulfur, instead of 16, will now have 18 electrons, which will also be 1s2, 2s2, 2p6, 3s2, 3p6. That again is, in this case, argon's configuration. So when you have something that has a charge, you have to adjust the number of electrons. Again, positively charged means take away electrons from your total. Negatively charged means add them to your total. And what we see here with both of these elements, which are representative elements, they both ended up at the same electron configuration as argon. Yeah. So sulfide, potassium ion, and argon all have the same electron configuration. And that is what is referred to as being isoelectronic with each other. Isoelectronic means these are things that have the same electron configuration. This makes sense because, frankly, if you put potassium and sulfur together, you will make an ionic bond, right? And the purpose of an ionic bond, as we talked about, is for everybody to reach the noble gas configuration, right? And that is how they do it, right? By losing and gaining an electron. So when representative elements like metals, when they typically lose electrons, they will back up on the periodic table to the same electron configuration as the noble gas that comes before them. And non-metals that gain electrons in an ionic compound will go forward to the noble gas that comes after them. And again, that was the whole point of the bonding that we talked about. That allows everybody to get to that noble gas configuration. Question on that there. So the electron configuration for, say, magnesium with a +2 charge, what should it be? Or why don't you write it? And why don't you also do oxygen with a -2 charge? Where's the electron configuration for both of those? Okay, so let's take a look. So as we see here, magnesium is 12, which means when it has a +2 charge, we need to lose 2 electrons, which means it should have 10, which should take us to 1s2, 2s2, 2p6. R, that is neon's configuration, as it has now basically moved backwards on the periodic table and hit the noble gas that comes right before it. Oxygen here has 8 with no charge, and a -2 means that it will also end up with 10 electrons, which means for that guy as well, it would be 1s2, 2s2, 2p6, our neon's configuration. So once again, both of these guys are isoelectronic with neon. They all three have the same electron configuration. This is what we were talking about earlier when we were doing bonding. They do not change into those elements, but in terms of electrons, they end up being the same as how that noble gas has its electron configuration. And since noble gases are very stable, that again is the purpose of the ionic bonding, and any bonding is for them to sort of arrange their electrons in the same fashion. Any questions on things with charges now? Okay, then let us take a look here. Talk a little bit about transition metals. So transition metals are a little bit different in a sense, and they're different in a sense of, as we'll talk about in a second, how they lose electrons, but just in how they fill them. Transition metals start with d orbitals. So they were really the first ones that you hit the d orbitals in when you get there. So they have incompletely filled d orbitals or completely filled d orbitals. And when you go through that little kind of zigzag order of how to put electrons into the atom, there is a few exceptions that you'll run across when you get into the transition metal region, which is again on the periodic table between group 2 and 3. The center part is our transition metals. Two major exceptions that you should be aware of is chromium and copper. And chromium is 24 and copper is 29. If you strictly, for example, followed the zigzag pattern for chromium, you would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4, which is basically, if you come through here, argon, 4s2, 3d4. It has been found experimentally to actually have one more electron in the d orbital versus the s orbital. And the correct electron configuration is what we see down here, 4s1, 3d5. What that essentially does is it throws one electron in each of the d orbitals in the upward position, right? So it's super maximizing the parallel sort of spin and stability. Copper is similar. Copper at the end also has one less electron in its s orbital and one more electron in its d orbital, and it's found to be more stable in that situation. This happens really because the s orbital, like the 4s orbital, and the 3d orbitals are really close in energy. So it doesn't take a lot for electrons to kind of jump up and down in terms of energy. What actually happens, as we'll talk about here in a second, is when you actually start putting electrons into the d orbitals, there's actually a switch in energy that happens between these orbitals. And it ends up being that the 4s will actually end up being higher in energy than the 3d. And that only occurs as you start populating, after you populated the d orbitals, they kind of switch in energy. That is also why sometimes if you Google it or look online, you'll see people that will write electron configuration like all in order, like all the 2s are together, all the 3s go together, and then the 4s. And that's because the electron configuration is written in terms of energy. I would say probably 99.9% of the time when you take a chemistry class, like all the chemistry classes you'll take here, you always write the electron configuration in terms of filling order, which means the s is actually lower in energy first, so they should get the electrons and then the d's. But sometimes you'll see people kind of write it in terms of energy, which is like after the electrons are there, and you'll see it kind of switch. So for us and pretty much all the chemistry classes you take, you should always write it 4s, 3d, and follow that pattern on the zigzag thing. In addition, there's a lot more exceptions to electron configuration. So if you look at the periodic table and you look where chromium is and copper, 24 and 20. For the transition metal region, there's a lot of similar type of exceptions, like silver is an exception. It has actually no electrons in the s or anything like that. But for us, and probably most of your chemistry classes, these are the two that you should know. So for us, it's just the exception for chromium and copper. For anything else in the transition metal region that might be an exception, you'll write it like normal. Chromium and copper, you should know those two exceptions. Any questions on that there? And here's an example of some of those other exceptions that I was just talking about. So there's our chromium and copper. And again, you can see in the case of PD, there's like no electrons at all in the s. They've all been promoted upwards to the d. So kind of right below those guys, there's a lot of similar exceptions. But for us, these are the two that I guess I should circle the right one here. These are the two, which is the correct one there on the right, that you should know. Any questions on that there? So the lanthanide series is where our Fs basically start to happen. And that is going to have completely filled or incompletely filled 4F or 5F subshells. So while we're talking a little bit about transition metals, let's talk about what happens when they actually lose electrons. So it's slightly different than the ones we just talked about. So because they're transition metals, they will lose electrons and basically become cations and positively charged. And it has a lot to do with what I just drew, which is our 4s and our 3d. And then we kind of put our electrons here, and then these guys switch energy. And the 4s, again, becomes higher in energy than our 3d. So when we take something like iron, for example, which is number 20, where 1, 2, 3, 4, 5, 6. If we write the electron configuration for iron, it would be argon. So I'm just going to kind of shorthand it there, which would take us to 18, 4s2, and 3d6. So this would be the electron configuration of iron with no charge. And what will happen with iron with no charge is it will have this switch that will occur. And after the electrons go in there, its kind of ending orbital diagram will look something like that, right? With our 2 in our s and our 6 there in our d. So when iron becomes something like a +2 charge, it actually will now have 24 electrons, right? Because it lost 2 electrons, is why it's +2. Because there was a switch in energy, which happens with all transition metals, electrons are always lost from the highest energy level, which in this case is actually going to be the S. So even though we put them in the D at the end, now that they have switched, the S is higher in energy, and we will actually lose these electrons first. And the correct configuration would be argon 3d6. So transition metals will always lose those S electrons first because of that switch in energy that occurs. And then if they need to, they then can delve into the D because they have more electrons. So in the case of iron, if I had iron 3 instead of 2, it would have 23 electrons. And when it would go to lose those 23 electrons, it would take out, just like the one above, these two. But now it needs to go in and take out one of those in the D as well. So we're going to take out one of those in the D. And that will leave us an electron configuration of argon 3d5. So unlike representative metals where they lose electrons and they end up back at the noble gas configuration, transition metals don't end up there because it's too far away. So they actually will always lose those S's first for all transition metals. Then if you need to lose more, you should delve into the D. Any questions on that? So why don't you try one? What is nickel's configuration? And what would be the configuration for nickel with a +4 charge? Nickel there is 28. Here, I'm going to go shorthand. So I'm going to go argon, which represents obviously 18. And we will then have 4s2, and then we could get into our d orbitals afterwards, and that's like 3, 6, 8, I believe. So that is the electron configuration there for nickel with no charge, and sort of the noble gas configuration. Any questions on that? With a +4 charge, that means it has lost 4 electrons in this case, which means it will end up with 24 electrons necessary. So in this case, once again, because it's a transition metal, it's going to lose the 2 electrons here first. And then to take the extra 2 out, it will have to delve into that d orbital. And in that case, it will leave us with argon. We lost all the s orbitals, electrons, and now we will be left with just 6 in terms of our d orbital. Any questions on that one there? So again, transition metals is a little bit different than how sort of representative metals lose electrons. All you have to remember is always take the S, and then if you need more, go into the D to remove them. Any question on transition metals in terms of how they lose electrons? All right. So let's talk about the periodic table. And if you are good, I guess, or if you're careful, I guess is a better way of saying that. If you're careful, you could actually just count off electron configuration from the periodic table if you kind of know what you're doing. And when we look at the periods, there are 7 periods that head this way. And those period numbers are pretty much the n numbers. So that's like n equals 1. This here would be like n is equal to 2 and so forth. And when we look at the periodic table, the first 2 groups are the s block, and that's because s orbitals could hold 2 electrons, right? So 1 electron, 2 electrons, basically. If you look from group 3 to 8, that is the p block, and that's because p subshells can hold 6 electrons. 1, 2, 3, 4, 5, and 6. The transition metals are the d orbitals, which could hold 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And those 2 guys on the bottom there, the lanthanide and actinide series, is the F block, which could hold 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So you could actually count off electron configuration by just looking on the periodic table. So for example, here, if we were to go to sodium, which we did before, I think, we would start at the top and this would be 1s2 to there. We would then continue on. This would be 2s2 to there. This would then be 3s or 2p6 to there. And now 3s1 right there at sodium. So you could actually just count it off. We also maybe did sulfur as well. So if you wanted to go to sulfur, bless you, you would start up on top. This would be 1s2 to helium, 2s2 there to beryllium, 2p6 to neon, 3s2 to magnesium, and now we're at 3p1, 2, and that's 3 and 4, right? So 3p4 there for our sulfur. Question on that. You do have to be careful. For example, we just did nickel, I think. Yeah, so we just did nickel. And nickel, if we were going to count it off, for example, would be 1s2, 2s2, 2p6 to neon, 3s2, 3p6. This would be 4s2, and this would be 3d. 1, 2, 3, 4, 5, 6, 7, and 8. And that is because the d orbitals start on the third energy level. So that's actually 3d there. That's 4d, that's 5d, and 6d. The d's are one behind the period number. So you got to make sure you account for that. That also means that if we were to look at these guys down here, if you remember, based on atomic number, they go right about there. This would be 4f and 5f, because that is where f start. And technically speaking, they would be here, which is actually 2 behind the period number. So f is actually 2 behind the period number. So if you're careful, you could actually count it off on the periodic table. It does get a little dicey as you get into the transition metal region. You got to watch out for the numbering and stuff like that. And definitely if you get down into those Fs, you know, it gets a little crazy in that. My best piece of advice is to still use the zigzag thing that we used earlier to do it. But if you want to kind of quickly do it, if it's a representative element or a transition metal, you know, you can kind of quickly look at it to check yourself and count it off on the periodic table. Any questions on that there? All right, questions on electron configuration? Yeah. Yeah, so no, so what we talked about there, they start, and why it's broken up like this is on the n equals 1, there's only s orbitals. That's where it starts. On the n equals 2, you also have s orbitals, but that's the first time that p orbitals appear. On the third energy level, you still have s and p, but that's the first energy level that d's appear, which is why this guy right here is our first d, so it has to be 3d. And on the fourth energy level still has S, P, and D, but that is where you first start to see F appear, which is why this guy down here is actually 4F, because that's the first appearance of F orbitals. Even though period-wise, it is 2 behind, and D is 1 behind the period number. Question on that? All right, seems like a good place.